morning, everyone watching pre-calculus today. So we have entered the last phase of our pre-calculus course for the semester. And this is the phase in which we get introduced to the last type of function model that we're going to study in pre-calculus. It's the last one in the sense that that the models that we study from here on out are going to be no more sophisticated than the ones that we're looking at right now. But in a way, it's the first kind of function model that's going to introduce a new type of arithmetic into the functions and the formulas that define the functions that we use. Up until this point, we've been studying what you might call, broadly speaking, the class of rational functions. The class of rational functions are the functions that we can build just by using the four fundamental operations of arithmetic: addition and subtraction, and multiplication and division. All of our linear, polynomial, quadratic, rational functions we've been studying so far can be built out of the variable x, for example, as well as just those four operations: addition, subtraction, multiplication, division. So what we want to do to round out our toolbox of functions that we can use to model processes of relationships and change that we measure in the world is we want to round out our study by looking at one level higher on the arithmetic layer cake, by looking at functions we can define not just with those four operations, but also with the operation that we built on top of repeated multiplication. In other words, the operation of exponentiation, exponentials. So what can we do if we also incorporate into our mix of arithmetic that we can use to define our functions the exponents, the roots, and the other inverse of exponentiation, which we get introduced to today, which are logarithms. So over the course of these next two, which are our last two live streams of the semester, we're going to tackle the notion of exponential functions. What are they? How do they work? How do we do algebra with them? How do we model change processes with them? What are the important parameters? How do we interpret those parameters in context? And so forth. So here's the agenda for the first half of that exploration, which we'll do in today's live stream. First of all, when we talk about exponential functions, we very often think about them as modeling either processes of growth or processes of decay. So either, respectively, we're going to be modeling behavior that looks like it increases as the value of x increases, or decreases as the value of x increases. So unlike our polynomial and rational functions that we just finished our study of, exponential functions don't have the ability to change direction at any point in their relationship. They're what we call monotone or monotonic functions. Their graphs are always going in the same direction. In the case of exponential growth, the direction that every exponential growth curve goes in is what we call an increasing direction, right? As we increase the value of x, the value of y increases. Or, conversely, exponential decay, in which as the value of x increases, the value of y always decreases. So in a way, the graphs of exponential functions are much more boring compared to the graphs that we just finished studying of rational functions that can do all of these funny things. They can have all these vertical asymptotes, horizontal asymptotes, and holes, and they can change direction. They have all these different turning points and everything. Exponential graphs just always go in the same direction, either always increasing or always decreasing. But you'll notice that exponential growth and decay curves do actually have horizontal asymptotes. They just only have them in one direction. So it sort of settles down to the x-axis as we go to negative infinity in the case of an exponential growth curve. Or for an exponential decay curve, it settles down to the x-axis as a horizontal asymptote as x approaches positive infinity. So we will still be able to talk about a little bit of the interesting graph features that we had with rational functions, just not nearly as interesting for exponential functions. So why exponential functions are in fact really interesting is that they have the ability to model new types of behavior. So the first thing we want to wrap our heads around is how do we spot exponential behavior in data and in words? So how do we know it when we see it? The most important contrast here is going to be able to tell the difference between exponential behavior on the one hand and linear behavior on the other hand. And the key to understanding the difference between exponential behavior and linear behavior is going to be understanding a difference in arithmetic. For exponential functions are going to relate together changes in the x variable, the independent variable, that can be explained by addition and subtraction, with changes in the dependent, the y variable, that can be explained not by addition and subtraction, but by multiplication and division. So that is the key distinction. For linear functions, addition and subtraction in x is interchanged with addition and subtraction in y. But for exponential functions, addition or subtraction in my x variable leads to multiplication or division in my y variable. And the simple reason for that is the fact that we learned when we talked about the exponent properties way back in our algebra experience last semester, for example, that when I multiply together two powers of a common base, what happens to their exponents is that their exponents add. So multiplication of powers leads to addition of exponents. And that simple algebraic truism is the explanation for why exponential functions will be able to relate multiplication in their outputs to addition or subtraction in their inputs. So that is going to be the key shift in paradigm. It's going to change how we look for exponential behavior in a data table. It's also going to change how we communicate about exponential behavior when we put that information into or out of the written word. Also, graphically, how are we going to be able to spot exponential behavior in a graph, other than the fact that we have this curve that looks like it's always increasing, or this curve that looks like it's always decreasing? Is there a way that we can spot when one of those increases or decreases really does interchange addition in the x with multiplication and division in the y? And so we're going to look at a nifty tool called semilog graphing that can actually help us to expose that difference and be able to really draw the parallel between exponential behavior that we're interested in today and the linear behavior that we're more comfortable with from a couple of chapters ago. So that's the first big question, is how do we spot this kind of behavior when we see it? And then once we've fully explored the graphical, the verbal, and the numerical, the data table perspectives on exponential functions, we of course also need the algebraic perspective. How do we write down an equation for an exponential function? And what are the important parameters that we can put into that equation and then interpret in a verbal context? So we're going to look at two different ways to write down an exponential equation. The first one directly uses the two salient parameters of an exponential relationship, the base and the intercept. And the base and the intercept of an exponential equation can both be found in this form of the equation. The intercept, which just like for linear equations is the y value of the y-intercept of our equation, can be found right out here in the front. I'm going to call it capital A for today. And the base of the exponential expression, this is going to be the surrogate of the slope. When we thought about slope of linear equations, the corresponding notion for exponential equations is going to be the base. And the base of an exponential function, the base of an exponential expression, is going to be found right here. And the exponent on that base is going to be our independent variable. So one form of an exponential equation is going to be y, or f of x, equals a times b to the x. To me, this is the most illuminating way to write down the equation of an exponential function. But for a variety of both historical and technological reasons, it's very often convenient to re-express such an equation instead of using the base as some number b, which we can directly interpret. We can also convert that equation to have a different number in its base, and the number that we most frequently see in the base of an exponential expression is called the natural base, or the natural number. And that natural exponential base goes by the name e. So e is a number we're going to get an introduction to today. It's somewhere between 2 and 3, so it is just a number. But so many of our exponential functions are written in terms of that base that we also want to understand what is the relationship between these two. How do we work with an exponential equation that uses e as its base and adds a new parameter, which we're calling r here, as the coefficient of x up in the exponent when the base is equal to e. And this a out here in the front still corresponds to the intercept of that equation. So these are two different types of formulas that we can use to represent exponential behavior. And these two are very closely related one to another, right? If you look closely, you see that the only difference between these two equation types is that where one of them has the base directly written as b, the other one has e to the r. After all, e to the r, if I raise that to the power x, I'm taking a power of a power, and therefore I'm multiplying the exponents, which is exactly what's happening up here. And so the relationship between these two equations is that the base b is equal to e to the r. So we're going to call b the base. We're going to call r, we're going to give it a special name. It's going to be called the continuous rate for our equation, when my equation is written in this format. And so depending on whether we have an exponential growth behavior or an exponential decay behavior, this r could be called the continuous growth rate, or it could be called the continuous decrease or the continuous decay rate, depending again on the context. If you're a biologist, for example, you might use exponential behavior to model population growth or population decay. Or maybe if you're a biochemist looking at enzymatic action or something like that as it relates to temperature. As the temperature increases, the activity of your enzyme might increase exponentially, or it might decrease exponentially. So you could use that to model that type of behavior as well. If you're thinking about dollars and cents, if you're doing an accounting model or a financial model, or if you're looking at an investment or something, very often when your interest rate is constant, your growth or decay is also going to follow an exponential relationship. And this r is the interest rate, the continuous rate of increase in your investment, for example. So typically this r in the e to the r formulation gets reported in a lot of application cases. We want to understand how to do both of those things. And then finally, anytime we have a new type of algebra on the table, we not only want to know how to be able to simplify expressions that involve this kind of exponentiation, so simplify b to the power x or e to the r times x, but we also want to know how to be able to solve equations like this. How do I rescue an unknown x from out of the exponent in an exponential expression and get it back down to the base so that I can solve for it? That requires a new type of inverse that we haven't talked about yet. We know that if the base is the unknown and the exponent is a constant, we can just use a root or a radical, a fractional exponent, to rescue that unknown base. But when it's the exponent that's unknown, we need a different type of inverse for exponentiation, and that new type of inverse is called a logarithm. So if b to the power x is equal to y, then by definition, there's nothing more to this than just sort of giving a new name to this phenomenon, to this relationship, that the base b logarithm of y is equal to x. This is nothing more than the definition of logarithms. There's no deep mathematics going on right here. What it's doing is it's giving us the very same relationship between x and y that is expressed by the equation on the right is also expressed by the equation on the left. The only difference is the roles that x and y are playing in this relationship. Because on the one hand, here y is known and it's been solved for, and x is wrapped up in some arithmetic. Whereas over here, x is known, it's solved for, and y is wrapped up in the arithmetic. But both of these boxed equations here are representing the very same thought, right? They mean exactly the same thing. One of these equations is true if and only if the other one of these equations is true. And so all it's doing is reversing the roles that x and y have in this relationship. And so what that's going to lead us to wrestle with first is, how do we reverse the roles of independent and dependent variables in a functional relationship? So before we even talk about the specific examples of exponential functions and logarithmic functions, we're going to worry about how do we do that back and forth. If I know how x determines y, how do I know how y in turn determines x? So that's going to be our first set of topics when we talk about composite and inverse functions at the outset. Also, one of the main things that's going to differentiate today's lesson from our next lesson, which is going to be our last one for the semester, is that the bases that we're mostly going to study when we talk about logarithms today are base 10 and base e. To be able to use other types of bases, we need a little bit more understanding of the properties that logarithms have, the algebraic properties, which come from the algebraic properties of exponents. But that's the topic that we're going to really sink our teeth into in our last live stream of the semester when that comes up at the end of the week this week. So for today, the bases that we most care about are base 10 and base e. So let's get things started by thinking about composite functions and inverse functions. This is really a question of how do we reverse the roles of x and y in a relationship that's expressed as a function in some way. So how do we go back and forth? So the question of composite and inverse functions tends to look something like the following. So say that I have two functions, a function f and a function g. And I just want to take a quick moment here and just think about these functions by themselves first before we start asking more sophisticated questions about them. So here's a function, f of x equals x over x minus 3. And I've supplied a graph here as well. So we have this function from both the algebraic perspective and also the graphical perspective. Just use some technology to get this graph right here. And secondly, I have another function, g of x equals x squared minus 4x. So I have two functions right here, and I'm seeing the graphs of both of them, just right off the bat. So once I have the graph of a function, I can already answer a lot of interesting questions about it. I can do really basic things. Remember how we use a graph to do something like evaluate what is f of 6 or something like that, right? If I want to know what f of 6 is, I can, using my formula, just plug in the value 6 in for x and just do 6 over 6 minus 3. 6 over 3, that's equal to 2, right? So on the one hand, that's my algebraic perspective. I can just use the formula and just plug and chug, right, to be able to answer the question, what is f of 6? But I also have a graph, and I can use the graph to also give me an answer to that same question. After all, the 6 that I have right here, this 6 is really a value of x, right? So this 6 is really an input to my function. And so if I want to use my graph, then what I want to do is I want to find x equals 6 on the x-axis and ask what point on the graph of my function, and on a graph, remember, every point's y value is equal to f of that x value. I just want to know what y value has the x value of 6. And so from my x equals 6, I plant my feet and I look above and below and ask, is there a point on the graph either above or below x equals 6? And in this example, the answer is yes, there's a point directly above x equals 6 on the graph of this function. And then to find the y value, all I have to do is read off the y-coordinate of that point. And the y-coordinate of that point is 2, right? And so that f of x value that we got out of this function is really a y value. And the ordered pair of the point on the graph that corresponds to the question that we just answered, right, is the ordered pair 6, 2. That ordered pair is on the graph exactly because f of 6 is equal to 2. So that's the basics, right, of how we get information into and out of a graph. We could do the same thing with the g of x graph over here if we wanted to as well. So that's all well and good. How are we going to, though, take these functions and use them together in some way? Right. So here's an example of a few questions that we might want to answer about these functions. Get over here on the top of the page. So I've written down some expressions up here on this, on the top of my screen here, that incorporate both the function f and the function g, okay, in a sort of one after the other fashion. So let's take this first example up here. I've written an expression that says f of g of 3. So if I want to understand what this expression means, I first have to remember the order of operations tells me that when I have nested sets of parentheses, as I do right here, that I should go to the innermost set of parentheses first and begin the evaluation of this expression from there. So if I read this as f of g of 3, then what I'm really supposed to do is first take the number 3 and evaluate the function g of x for the input value x equals 3. So what is this really telling me? This is really telling me to take the value x equals 3 and evaluate my g function at that value. So that means that on the graph of g of x, I'm going to start with x equals 3. I'm going to look above and below that point and see if there's any point on my graph of g of x that's above or below that point, and sure enough, there is. I'm going to move my number 3 up here just so it's a little easier to read. There is a point on the graph that has an x-coordinate of 3, and therefore we can evaluate g of 3 just by looking for the y-coordinate of that point, and that y-coordinate, according to my graph, is -3. And so at least according to my graph, when I evaluate g of 3 is equal to -3. And so, in my expression up here, I simplify g of 3, and g of 3 gives me -3. But I'm not done, right? Because in the rest of my expression here, I'm supposed to take that -3, which I got from evaluating g of 3, and make that the input to my f function. So the y that I got out of this g function becomes the x that I'm going to stick into my f function. So negative 3 now becomes the x value, and it's behind my head here, the x value at which I now want to evaluate the function f. So the old output becomes the new input to my function. I've strung these two functions together. The output of g gets fed into the input of f. And then I do the same process with my f function, where I look above and below x equals 3 on the graph. I find out that there is indeed a point on the graph of f of x that has an x coordinate of negative 3. And I just want to know what's the y coordinate that corresponds to that point. So I look over to the y coordinate of this point, whatever it is, and it looks to me like this is about 1/2. 1/2. Looks like it's equidistant between 0 and 1 here. I'm kind of estimating from this graph, but we'll verify using the formula in just a moment. So f of negative 3 becomes 1/2, and therefore 1/2 becomes the result of the composition, is what we call this, of f of g of 3. So what we've done, really, sort of in spirit, in the moral of this story, is that if we think about functions as being like input-output machines, as I very often like to do, then both f and g are machines in and of themselves. Right? So if I give these two machines names, here's my f machine, here's my g machine. Actually, let me reverse those so we can read this from right to left. Then what really happened here is we really took the number 3 and we used it. Where's my pointer? Here's my pointer. So we took the number 3, we used it as an input to my g function. So we put 3 into my g function, and out of that g function came an output of negative 3. Right? That's what happened over here. But then that negative 3 became the input to my f function, and when negative 3 is the input to my f function, the output from my f function was 1/2. So that's really what we're doing when we're forming a composite function, is we're just sticking the output of the first function into the input of the second function. And then that's all that we really need in order to form the composition of two functions. So what I want to do next is just invite a guest lecturer back to our table here. This is Brian McLogan. We got an introduction to him a few live streams ago. And he's got a quick rundown on what composition of functions looks like from an algebraic perspective. So let's take a look at his video. We're going to watch. It's just going to take about 3 or 4 minutes, and then we'll come back and we'll bring it back to the rest of our examples that we see here for composition of functions.
Welcome, ladies and gentlemen. So what I'd like to do is show you how to compose two functions. And basically, when composing two functions, we're going to have two functions. Let's say f of x and let's say g of x. Okay. Now, composing basically means we're going to plug one function into the other. So really the best way, I think, and the easiest way to understand this is just to go back to evaluating functions. When we first started learning about functions, we learned how to evaluate them. So for instance, we have a function f of x. F represents the name, and then inside the parentheses x represents our input variable, our input value. And then we have some sort of rule that is going to represent the function. And for instance, let's just do 2x minus 3 is our rule. So x is our input value. Here is our rule. Now, when we change x in our input in our notation, we're going to replace it with our rule, and then we'll be able to find the output value. So our input value, here is our rule, and then once we evaluate it, that's going to be our output. So for instance, if we wanted to figure out f of 1, now what we're going to do is replace our input variable here with the 1, and then we can evaluate that to get our output. So we plug in 1, 2 times 1 is 2. 2 times 1 is 2, minus 3 equals -1. And you can think of functions, again, as like the input-output. We can write this as a coordinate point here, 1 comma -1, where x is my input, -1 is my output. And we can kind of continue this pattern, kind of picking up any really numbers that we want. And we just kind of do the exact same thing. I don't know why I'm having a problem writing those down. That equals 1, so therefore this input-output would be 2 comma 1. And basically what we realize is no matter what we're going to place in here in the input, we're always going to plug that into our function. So no matter what number. But we don't just have to deal with numbers. We can start getting kind of creative, and getting creative on things that maybe won't make as much sense. So for instance, I could pick up f of triangle. Well, that would be 2 times triangle minus 3. Now, we can't really evaluate 2 times triangle minus 3, so that would be our exact output. Or we could also do like expressions. For instance, f of negative x. That would be 2 times negative x minus 3, which that would simply reduce to negative 2x minus 3. So it really doesn't matter what exactly we want to plug in. Whatever we plug in for our input is what we're going to replace here. And we could even pick, a different variable. We could pick f of a. So that is 2 times a minus 3. We can also do, expressions, x plus h. So that'd be 2 times x plus h minus 3. And we could obviously simplify that to 2x plus 2h minus 3. So you can see that the limits here are endless here of what we could plug into our function. So that brings us to our other point. F of, how about we plug in another function, f of h of x. Now we have no idea what h of x is. There's nothing written on the board here of h of x. But again, I would just follow the same steps. Okay? So where this gets interesting is once we start identifying what is f of x and g of x. So let's stick with the f of x function is 2x minus 3. But now let's call g of x. Let's actually give that a rule. Because up to this point, we were just saying f of x had a rule. G of x or h of x did not have a rule. Let's call g of x. Let's give this another rule. Let's just call this x squared. So therefore, if now I have the function f of g of x, well, now basically what I'm going to do is I'm going to plug in g of x, 2 times g of x, minus 3 like I did for h of x, but now I know what the rule is of g of x. So now I'm simply just going to do 2 times x squared minus 3. And that's basically composition. Now composition can also work the other way. We can also take f of x and plug it into g of x. So to do that, I'm going to take my f of x function and plug it into g of x. So therefore, it's basically going to be f of x squared. Yeah, that's it, f of x squared. So therefore, that's going to be 2x minus 3 squared. So that's really the basics of what we're doing. It's just like evaluating functions. You're plugging one function into the other. Just so you know, another notation for that would be like f of g of x. We use that kind of open circle. And for this one, it looks something like this. So just another way that you guys can see the notation for composition. But there you go, ladies and gentlemen. That is your basics for how to compose two functions. Thanks.
There we go. I'm back on with my microphone. So there's the quick rundown of how to compose functions, how to form the composite of two functions. So let's take that understanding back to the examples that we were working on right here, right? We're just plugging the output of each function into the input of the next one. So let's do g of f of 2 and try and get that evaluated as easily as possible. So since f of x is x over x minus 3, f of 2, so now we're going to be plugging 2 into the f function, evaluating f at 2. And so what am I going to get? According to my formula for f of x, I'm going to get 2 over 2 minus 3. And 2 over 2 minus 3, I evaluate that. 2 minus 3 is negative 1, and so I get negative 2 as the value that I get out of my f function. And then I'm supposed to plug in my negative 2 value into my g function. My formula for g is g of x equals x squared minus 4. And when I take negative 2 quantity squared minus 4, negative 2 squared is 4, minus 4 is 0. And so at the end of that process, g of f of 2 ends up being equal to 0. Now let's go in and form the full formula for the composition f of g of x. So if I plug an x into my g function, and then I evaluate the result of that evaluation through my f function, f of g of x, I'm going to be first putting x into my g function. And my g function is going to turn that into x squared minus 4. And so out of that function is going to get x squared minus 4. And then when I evaluate the f function with an input of x squared minus 4, so this actually is, let's zoom in on this for just a moment here, because I want to make sure that I'm explaining this as carefully as possible, is that what I'm doing at this point is I'm trying to evaluate not f of x, but f of x squared minus 4. When I'm doing f of g of x. And so if my rule for f of x is x over x minus 3, then everywhere where we have an x in this rule, we're going to replace it with x squared minus 4. And so I'm going to get here x squared minus 4 in place of my x upstairs, and downstairs I'm going to have x squared minus 4 minus 3. Right, see how I did that? In place of every one of these x's, we get an x squared minus 4. And now if I simplify this expression, I'm just going to have x squared minus 4 upstairs, and downstairs x squared minus 4 minus 3 is going to give me x squared minus 7. And so there we have a simplified formula for f of g of x, the composite function, x squared minus 4, all divided by x squared minus 7. Okay, so that's the lowdown on finding composite functions. This turns out to be really big business when we go into calculus, because one of the key skills that you're going to need in calculus is being able to identify when a function is a composite of other functions. It's going to be one of the key analytical processes that you're going to go through in order to understand a function well enough to do calculus with it. You're going to have to take it apart into pieces which compose back together to make that function. So the more practice that you get here working with composite functions, the more well positioned you're going to be to answer those questions in calculus when they come up next semester. So composite functions is just the beginning of the story. The next thing we want to understand is how do we take a functional relationship which relates x's to y's, and how do we turn it on its head? How do we take one of these function machines, and instead of running it from input to output, how do we run it from output back to input? If my function tells me how x's turn into y's, then how can I reverse that machine to turn y's back into x's? That process is called finding the inverse of a function. When we can do it, and we can't always do it, but when we can do it, the result of that process is called the inverse function. So I want to start just by asking a simple solve the equation kind of question, and I want to ask it for both my function f that we're seeing here on the left, and I also want to ask it about the function g over on the right. So starting from the function f, let's suppose that the task that I have in front of me is that I want to solve the equation f of x is equal to -2. So let's suppose that that's my goal, is I want to solve the equation f of x equals -2. How would I do it? Let's start by thinking about how I would do it using the graph of f of x that we see right here. Well, remember that my equation here is relating an x value and a y value. The x value that I don't know is what I'm calling x. It's someplace along the x-axis. But the y value, -2, is a number that I do know. And so what this suggests to me is that I should take the y value, y equals -2, and ask what point on my graph has a y coordinate of -2. That's another way of saying, let me draw the horizontal line whose equation is y equals -2, and ask if there are any points on this graph where the graph intersects with that line. And the answer is, yes, there is such a point. There's a point right here, where the y coordinate of my point is -2. And so if I'm trying to figure out what x value corresponds to that y value, all I need to do is ask, what is the x coordinate of this point? To do that, I just need to look above and below this ordered pair and ask, well, where on the x-axis does that point live? What is that x coordinate? And I find out, based on what my graph looks like, that the x coordinate of that point looks like it should be +2. So if I'm trying to solve the equation f of x equals -2, then according to the work that we just did, if I'm solving that equation, x over x minus 2 is equal to -2, that whatever algebra we would need to do in order to solve this equation, and we'll skip the specifics of that algebra step for the moment, that algebra would necessarily lead us, according to this graph, to the solution x equals +2. So this particular question, solve f of x equals -2, has a solution. It has exactly one solution. There's one place where this horizontal line meets the graph. It's the point 2, -2. So what's going to happen if I ask that same question not about the f function, but about the g function instead? Let's see if that changes the game, or if we have, a similar kind of story over here. So let's ask that question once again for g of x. If I were to give you this g of x function, g of x equals x squared minus 4x, and I were to ask you to solve not f of x, but g of x equals -2, what am I going to do? Well, once again, we can think of this from a graphical perspective as a relationship between an x value that I don't know and a y value that I do know. The y value that I do know here is y equals -2. And so I'll come down to my graph, y equals -2. I'll sketch a horizontal line right here, and I'll ask what point on the graph intersects with that horizontal line. But what we quickly find out is that there's more than one answer to that question. There is more than one point on this graph that has a y-coordinate of -2. There's this point over here on the right, but there's also a second point over here on the left. Both of them having the same y-coordinate, right? But they have different x-coordinates. And so that's actually an important enough observation that I want to pull that observation out right away. Before we get to the rest of the details here, is that here we have an example where the same y value has two different x values. And so when I solve this equation, g of x equals -2, I'm going to get two different solutions to this equation. And we know enough algebra that we could just do it. Right? X squared minus 4x equals -2. We could add that subtract that -2 from both sides to get x squared minus 4x plus 2 equals 0. We would hit this with the quadratic formula, and we would get x equals minus b plus or minus the square root of b squared, which is 16, minus 4ac, which is 8, so square root of 8, all divided by 2a, which is 2. We take the factor of 2 out of that radical. We get 2 plus or minus the square root of 2. And so if you like decimals, which I usually don't, but I'll make an exception for this one right here just to increase the clarity of what we're saying, one of my solutions is going to be about 3.414 for my x value. And my other solution is going to be square root of 2 minus the square root of 2, which is going to be 0.585 or so. 0.585. So I have these two different x values, both of which have the same y value, 3.414. Right? So qualitatively, there's a difference between what's happening when I solve f of x equals -2, where I got a single answer, versus when I solve g of x equals -2, where I got two different answers. And so the first thing that this tells me is that the f function, if we think of it like an input-output machine, my f function can be reversed, and that reverse is going to give me still a function. Any single value of x that I plug into my f function is necessarily going to give me a single value of y out the end, a single value of f of x, because f is a function. Single f of x. Because f is a function and its graph passes the vertical line test. But what we find out from this graph is that the converse is also true, that a single y value also corresponds to only one x value. So a single f of x value is going to give me out a single x value. And that's true because this graph passes the horizontal line test. Horizontal line test, again, meaning nothing more that every horizontal line that I can draw on the graph of f of x is only going to meet my graph a maximum of once. There's no horizontal line that meets this graph in more than one location. And so we can undo whatever f does. And so f has an inverse function. F is what we call invertible. So we're going to be able to come up with a formula for the inverse function for f of x. But the same is not true for g of x. Because if we imagine what g of x is doing, let me make some space down here, it's still true that because g is a function, every x that I plug in for my g function is going to give me the same, or is going to give me a single value for g of x. But the example that we have right here on the graph shows that there's two different values of x, that when I plug those x values into my function, I end up getting the same y value at the end, right? G of this number is equal to -2, but g of that number is also equal to -2. So even though g is a function, and so there's one output for every input, we cannot go backwards, because if we were to go backwards, my input of -2 would give me two different outputs, and that's something that a function cannot do. So g is not an invertible function. Because if there were a way to run this machine backwards, a single input would give me two different outputs, and that is something that a function by definition cannot do. So the horizontal line test is our trial to figure out how to determine whether or not a function even has a chance of having an inverse in the first place. So let's take a step back here, and we're going to start using this inverse notation to talk about the values of an inverse function when that inverse function exists. I'm going to return to the f example that we just did here, and we're going to look at that. Before we look at the general algebraic example, I'm going to invite another guest lecturer back to the table here. So we found out that on this graph that f of x is equal to -2 was synonymous with x equals +2, right? When x was equal to +2, f of x was -2. Or another way to say this, right, is that f of 2 equals -2. And so if I turn that relationship around, if I want to interchange the roles of input and output, how I could say that is that whatever the backwards function is going to take as its input -2, and it's going to spit out an output of +2. And we just have to give that function a new name. And the new name that we give that function looks like this, f with a little -1 up here in the top. This function is called the inverse of f inverse. And its job is just to reverse the roles of input and output that f had. Whatever f's inputs were are the outputs of f inverse, and whatever the outputs were are the inputs of f inverse. So all it does is it just interchanges those two things. Output becomes input, input becomes output. That's all there is to it, right? So the roles of x and y are reversed. And so when we have an invertible function, we should be able to find a formula for that invertible function. And how we do that is best explained by yet another guest lecturer. This is a YouTube video from a YouTuber called Nancy Pie, and she's going to go over the process of finding the inverse of a function algebraically. Let's take a look. This is going to take about 4 minutes or so.
Hi guys, I'm Nancy, and I'm going to show you how to find the inverse of a function. What's an inverse? An inverse is just the reverse of a function. It basically undoes whatever your function did. So if your function takes x and gives you y, your inverse function is taking that y and giving you back x. Why would you want to do this? Good question, I don't know, but your teacher wants you to, so let me show you how to find the inverse function. So what you'll already need to know is how to tell if something is a one-to-one function. So for every x value, you only have one corresponding y value. Okay, so say you have a function like this, f of x equals x plus 2 over x, and you need to find the inverse, if it exists. Of course, for this function, we also need to keep in mind that x cannot equal 0 because we can't divide by 0. The first step is just to rewrite f of x as just y. So we would just have y equals x plus 2 divided by x. Then, this is the most important step, you need to swap x and y. So you switch x and y everywhere they appear. So we would actually have x on the left side instead of y. Here on the right side, replace x with y everywhere. So we would have y plus 2 divided by y. Last step, you need to solve for y so that we're back to y equals, with y alone on the left side. To do that, we'll need to clear this fraction. So you would multiply both sides by y to clear the fraction, and then get in the next line x times y equals just y plus 2, because we've cleared the y. Then, if you want to get y alone, you'll need to have all your y's on one side. So why don't we just bring this y over to the left by subtracting it from both sides. So you get xy minus y equals just 2. Now, to solve for y, you only want y to appear once on the left side. So the best way to do that is to factor out a y. So you'd have y parentheses, and what's left is x minus 1 equals 2. Final step, divide out the x minus 1 from both sides, so you have y equals 2 divided by x minus 1. To write this as a function, we would use inverse notation. F inverse with a -1 superscript of x equals the expression. But first, you have to check that this is actually a function. Sometimes it's just a relation and not a function. Is this a function? It is, because for any one x value we plug in, there's only one corresponding y. And if we look at the graph of this function, as you know, it would look something like this. So if you did the vertical line test and checked everywhere, it only intersects once, so it's a function. So we can use this notation, f inverse of x equals 2 over x minus 1. If you found that it's not a function, you would just answer inverse function does not exist. So your answer for the inverse function is of x equals 2 over x minus.
All right, so using that very same process, let's take a look at how to find the formula for the inverse function of this f of x. Actually, the example from the video is very similar algebraically to this one, so we're going to kind of cruise on this. So to find a formula for the inverse function just interchanges the roles of x and y. So I'm going to replace my y by x, and I'm going to replace my x's by y's. So y over y minus 3. Just interchanging input with output. And now I want to try to solve this equation for y, which I can do by multiplying both sides by y minus 3. Whoops, my head's in the way. X times y minus 3 is equal to y. And then I'll distribute that multiplication, so I get xy minus 3x equals y. I'll move all of my y terms to one side, so I'll subtract y from both sides. I'll also add 3x to both sides. xy minus y equals 3x. Then I'll factor the y out of the left-hand side, y times x minus 1. And then my very last step is to get y by itself by dividing both sides by x minus 1. 3x over x minus 1. Whoops, and it's just a little bit down off the screen. Let me nudge it up. There we go. And so there is a formula for the inverse relation. And again, as she was saying in the video, because it's still true that every x value gives me only a single y value out of this, this inverse relation is actually still a function. So we don't have to worry in that example about the inverse not actually being a function. So there we have a formula for the inverse. F inverse of x is 3x over x minus 1. So what would have happened if we did the same process with our g function over here? Why does that work differently? We claimed the g was not an invertible function, but what would happen if we tried to find an inverse for g of x instead? Let's take a look at that before we close the book on this and we go forward to our next few examples. So here's my formula for g of x. G of x is x squared minus 4x. So if I'm using the same process, what would I do? I would put a y on the right-hand side, and then I'd have x squared minus 4x on the left-hand side. Oops, I think I interchanged right and left there verbally. X squared minus 4x. I would interchange the roles of x and y, so I'd place x over here. I'd place y's in place of the x's. Y squared minus 4y. And I would try to solve this equation for y. it's not the happiest thing in the world. I would subtract x from both sides. I would get y squared. Let me keep my colors here for a second. Y squared minus 4y minus x. This is a quadratic equation in the variable y. And so to solve this equation, I'm going to use the quadratic formula. This is going to look nasty for just a minute, so fair warning. I use the quadratic formula, and I find out that y is going to equal minus b, so that's 4, plus or minus the square root of b squared, which is 16, minus 4ac, which is going to be plus 4x. And then all of that is going to get divided by 2a, which is 2. And just to simplify this out a little bit, we can factor a 4 out of that radical. So I'm going to get 2 plus or minus the square root of 4 plus 2x. No, 4 plus x. So 2 plus or minus the square root of 4 plus x. So there is an equation for the relation of x and y that is the inverse of my g function, x squared minus 4x. But notice I can't write this as a function g inverse of x. And the reason that I can't write it as a function is because it takes more than one value generically for any given x, because of this plus and minus that's happening here. One value of x may have, in general does have, two values for y. And so there is no function which inverts this g of x. We'll just say that this inverse function does not exist, as the guest lecturer was just telling us at the end right there. And before I move off of this topic, I want to look at what the story is about inverse functions just from a graphical perspective. And that's actually going to be, we have to wrap up this live stream for today. We'll come back and do the second half of this in one more video later on tonight, because we got to get to the exponential and logarithmic functions. But to wrap up this portion of today's stream, let's go into a graphing tool so that we can look at what this relationship between the graph of a function and the graph of its inverse function actually looks like in general. So first, let's take the function that we discovered was, in fact, invertible from our video before. That was f of x equals, and let me get my formula back here for a second. F of x equals x over x minus 3. Okay, so that was this graph that we were looking at earlier. Let me make it a little bit more legible here on our screen. So here's f of x equals x over x minus 3. We discovered that a formula for its inverse, I'm going to call it, let me call the inverse I of x. We discovered a formula was I of x equals 3x over x minus 1. Okay, and let me set that graph in a contrasting color here just so that it's easier to see. Okay, so here are graphs, respectively, of the function f and inverse function, which we called I. I'm going to put the formulas for those on here just so we can see them as easily as possible. So f of x equals, I'll put the formula for f in here. And then I also want f inverse of x. And I'll put the formula for the inverse in here as well. All right, let me move those into position. And then what we want to know is what's the relationship between those two things. Get my color coding here. And then this was my graph of the inverse. All right, so I'm making stuff on the fly here. Okay, great. So here are the two graphs. And the first thing that I notice about the graph of f and the graph of f inverse is that they seem like they generally have the same shape as one another. They both have this sort of hyperbola, you know, these two curves that are sort of set in diagonals to one another kind of shape. The other thing that I notice is where these graphs intersect one another, that there are 2 points, 0, 0, and also 4, 4. If I label both of those points, take a look. These graphs intersect at those 2 points. And those 2 points just so happen to have the same x value as their y value. That's not an accident, right? Because if f turns a 4 into a 4, then its inverse will also turn a 4 back into a 4, right? Same thing with 0. If f turns a 0 into a 0, then its inverse will go backwards, but also turn a 0 back into a 0. So these two graphs are going to intersect exactly where the value of x and the value of y is the same. And all those intersections lie along this diagonal line that we call the line y equals x. So let me get a label in there as well. Y equals x. There we go. So that diagonal line, y equals x, is where we're going to find any of the intersections between my two graphs. But in fact, something more profound is true. Let me take all of my axes away here, except for that diagonal line y equals x. If you take a look at these graphs, there is a symmetry in these graphs. Namely, there is a symmetry of these graphs reflected across the diagonal line y equals x. And that is the relationship between the graph of a function and the graph of its inverse function. So that relationship is that the graph of the inverse of f is exactly the graph of f itself reflected across the diagonal line y equals x. So there's the moral of this story, right? That is how the graph of f is related to the graph of f inverse, when f is an invertible function. So what goes wrong if my function was not invertible? Let's go back to that. So for my g of x was x squared minus 4x. Hold on, I think I should probably reset my grapher here. We'll start fresh. So what happens when I try to graph the inverse of a function that's not in fact invertible? X squared minus 4x. So there's the graph of my x squared minus 4x function. And the inverse of that was, we decided, 2 plus and minus. So there were these two different, well, let's go at this a slightly different way. Let's replace g of x with y, right? Y equals x squared minus 4x. That's the graph of this function that we're seeing right here. Let me take the label off of that. And let me put in for a label y equals x squared minus 4x. Oops. There we go. So there's the graph, y equals x squared minus 4x in blue. And so what we do when we reverse the roles of x and y is we had the equation x equals y squared minus 4y. So I reverse that, the roles of x and y, and we're supposed to get the graph of an inverse relation. But what does that graph end up looking like? X equals y squared minus 4y. Well, let's take the label off of this here for a second. And let's give this a different color. There we go. So what's happened here? The inverse relation to y equals x squared minus 4x is x equals y squared minus 4y. But the big difference is that this inverse relation no longer passes the vertical line test. There are a lot of vertical lines that I can draw. There are a lot of vertical lines that I can draw that intersect this orange curve in more than one place. And so my inverse relation fails the vertical line test and so is not a function. So let me get this typed in here just so we can all see it. Inverse fails the vertical line test. And so the inverse is not a function. But the reason that that happened is because the original failed the horizontal line test. right? My big head is in the way once again. But just to drive this point home, right? Every vertical line that I can draw on the graph of the inverse is the same as a horizontal line that I would have drawn on the graph of the original function, right? Because we've interchanged the roles of x and y. So everything that was horizontal becomes vertical, and everything that was vertical becomes horizontal. And the relation to those, once again, is that they're reflections across the line y equals x. Y equals x. Right? Let me move that label once again, right? So there's the diagonal line y equals x. So every horizontal line on the graph of my original function corresponds to a vertical line on the graph of its inverse relation. And so because the original function failed the horizontal line test, my inverse fails the vertical line test, and so the inverse is no longer a function. So there's the graphical and algebraic rundown on how composite and inverse functions work. And that's where we're going to cut this video segment short. We're going to come back again later on this evening to do one more segment where we'll talk about exponential functions and get that introduction to logarithms as well. You won't want to miss that because we're going to borrow concepts from the video that we talked about just now about composites and inverses as a way of getting to the algebra of logarithms toward the end. So we'll see you in that next video when it comes along later on tonight.